I should probably start out by saying that this video is going to be a tad bit different in the beginning than my usual videos, but it's still about math, so yeah, just deal with it. So the other day, I was pacing around the house before a scheduled interview, and I thought I was ready. And by ready, I mean extremely anxious. Oh god, I should be prepping. How does that even work? I mean, you would know this if you actually used the Career Center in college. I mean, what if the phone rings and you just like hang up on accident? What do you do after that? I mean, or what happens if you just start cursing every time you make a mistake? I mean, it's fine. I don't need this job. I mean, I don't have to take the call. I can just ball myself up here on the cold, hard floor. And then I saw it. A light bulb. I mean, not an idea. Well, I mean, I did have an idea, but it was just an actual light bulb hanging there from the ceiling in a light fixture. And I found myself running over to the kitchen table where my scratch paper and pencil were. The thing that was interesting about the lighting situation was that we were in a fairly open room, and yet the light was not illuminating the entirety of it, which made me think of illumination problems. Now, the illumination problem has a solution, but I wasn't really thinking about the illumination problem, so we'll leave that for another time. Here is what I was thinking about. Let R, or whatever letter you want it to be a volume, that is, a room, and let L be a point in the volume R that represents a light source that emits rays of light at angles in the set theta. The question is, does the light fill the entire room, assuming that light reflects off the walls infinitely many times? It's a question that I don't really know the answer to, but my brain just kind of ran with it. Well, first off, illumination problems are closely related to their more straightforward relative, billiards. Mathematically, a billiard table is an open, bounded, connected domain such that the boundary is a finite union of smooth, compact curves. There's quite a few terms to go through here, and instead of just defining how a particle should move on the table and giving the definitions of each of those terms, we'll just give it an example. Let's look at this rectangular table. According to our definition, the boundary is the union of these four curves, which are just straight lines. And let's say that we're trying to hit the particle, or Q, in this direction. Then the trajectory of this Q would follow the line spanned by the vector until it hits the boundary, where the angle of incidence is equal to the angle of reflection. And then it would continue in a straight line along this path. The state space, or all the possible points and direction vectors for a billiard table B, is its closure crossed with the circle. The closure in this case just means that B is taken in union with its boundary, and the circle gives us all possible angles for the direction vector of the trajectory at that point in time. We can generalize this state space idea for a table that is in 3 dimensions too, where instead of a circle we have a sphere, and instead of a billiard table we have, well, I guess you could call it a billiard volume. Mathematically, it makes sense. Illumination problems consider all possible trajectories of a single point in the billiard space to see if the entire space gets lit. For convex regions and volumes, illumination problems are mostly trivial, as one definition of convex is that any straight path between 2 points is on the interior of the body. So, if light is emitting from the source at all possible angles, we would surely illuminate the space. Just pick the point that you're not sure is lit and draw the line from it to the source. That line segment is on the interior of your region by convexity. The problem becomes a bit more interesting if you consider restricted angles of illumination, or non-convex regions, which brings us back to a problem similar to what I was thinking about. I wasn't really able to spend much time on this problem because once I actually figured out what I wanted to explore, my phone rang. So, anyway, I hope that gave you a brief introduction to billiard problems and illumination problems. There's a lot more stuff that we can talk about with these things. You can look at billiards as like a dynamical system, and they have different ergodic properties, and illumination problems give a more like generalized billiard problem in a way. So there's a lot more I could talk about there, and we can leave that for another time. But if you enjoyed this video, make sure you give it a thumbs up. You can subscribe to this channel for more mathematics videos. I try to get these out every 1 to 2 weeks. I know it's kind of been sporadic. This is not my job, so it kind of happens when it happens. But anyway, As always, I am Nathan, this is Chalk, and I will see you next time.